Hi everyone, I'm Mark Hamilton, and I'm a research development engineer on the Microsoft Cognitive Services research team, and I'm also a PhD student in William Freeman's lab at MIT. Today, I want to share a project with you for deep interpretable visual analogies. This work is kind of designed to find connections across culture and media in the fine arts. So there's a bit of a backstory about this project. The kind of inspiration for this algorithm came from a trip to the Rijksmuseum. There they had an exhibit called Rembrandt and Velázquez that took works from Rembrandt and his collaborators and put them in dialogue with works from the great Spanish master Velázquez. And although these painters and their studios didn't have any contact and worked at opposite ends of Europe, they still painted incredibly similar scenes that really spoke to a deeper connection in the content and the semantics of these works. And so two that I found really impactful were this two juxtapositions, the martyrdom of Saint Serapion and the threatened swan. And although these are two very different subject matters, they still convey the same core idea. On the left here, we have Saint Serapion dying for our sins with his arms outstretched in a defensive and yet surrendering pose. And on the right, we have the threatened swan, again with wings outstretched, protecting her nest from an unforeseen enemy. And so, although these two works are incredibly different, they still speak to something very similar that both of these artists are trying to get at in their representation. And so we thought that this exhibit was really impactful and got everyone very excited about the connections between art. We were wondering if an algorithm could potentially scale this out and find connections not just between Rembrandt and Velázquez, but between any artist or culture or media across time periods, and really in a much more rigorous sense. And so, to formalize this notion, we realized that this algorithm would need to find visual analogies in the collection. If you kind of think about it, the martyrdom of Saint Serapion and the threatened swan are almost in analogy. Spanish is to Dutch, as martyrdom is to the threatened swan. And so to create an algorithm to kind of find these close matches, we need to do something a little bit like this. And this particular structure appears in a variety of different places in the machine learning literature. And perhaps the one that most people are familiar with is how it appears in text. So here I'll present a simple algorithm for textual analogies, and we'll see what aspects of it are similar to this problem and what aspects are a little bit different. The basic gist of this method is that you take a large corpus of words and you want to learn a representation for each word such that the core ideas in semantics are reduced down into a very small, tight representation called a feature. So the way you do this is that you play a little game. And the basic gist or the intuition behind this game is that a word gets its meaning from the company it keeps, aka a word's definition is in some sense learnable by looking at its surrounding words. And so in this case, the algorithm tries to learn representations for words such that you can take a word and predict its surrounding context. So in this case, we want to learn a function that goes from king to all the words that surround king, like the noble sat on his throne. And this function is parameterized. And when we learn this function, we learn representations for each one of the words that make up this sentence. And what's amazing is that these representations are useful for a variety of downstream tasks. And they also have a lot of hidden properties that people were really stunned when they discovered. In particular, they can answer the analogy question. And so, for example, if you had an analogy like man is to woman as king is to something, what you can do is find the embeddings for man and woman, look at their difference, and then apply that difference to the king embedding. And when you find the closest word that comes out, you find that it is the answer to this analogy, namely queen. So already we can kind of see that these intelligent embeddings sort of are able to get us close to this solution. And the only problem is that in the visual domain, we don't really have known pairs like man and woman. We've really used our intuition and our knowledge of English to be able to find this gender direction. But in the corpus of the Metropolitan Museum or the Rijksmuseum, we don't really have these pairs a priori, and so we need to use a slightly different method. So this method will involve a few new pieces of machinery that we'll hopefully be able to explore. And so, as a bit of an overview of what we'll be discussing today, we'll first discuss some of the building blocks of this algorithm, namely deep image retrieval, and we'll figure out how to specialize this system using a technique called conditional nearest neighbor methods. Finally, we'll evaluate this kind of approach using non-parametric style transfer. Then we'll see that we don't just want to find these close matches and analogies in the collection. We often want to understand why these particular systems are working the way that they're working. What is it that the algorithm is picking up on that makes this particular kind of visual analogy? So we'll explore how we can dive into the algorithm's brain and figure out a little bit more about what's going on underneath. Finally, we'll give you a little research snack and apply this algorithm to something completely out of left field, namely finding blind spots in generative adversarial networks. These particular spots are areas where GANs just fail to create data. You've seen these incredibly stunning images of human faces, and we'll see where GANs produce significantly less stunning results. So to understand how we can create a visual analogy system, we'll have to understand a little bit about deep image retrieval. And the basic idea is that you want to take an image, say your dog, and find the closest or most similar image within a collection of images like the Metropolitan Museum or the Rijksmuseum. And so to do this, we can't just compare distance in pixel space because that distance isn't very robust. It's very susceptible to things like small rotations or changes in brightness. So we can form a much better notion of distance by first taking this image and mapping it into deep feature space. The idea behind this is that you take a big trained vision network that already knows how to see and recognize images quite like a human being does, and you use the inner activations of this network as a new space to put your images in. Here, distance really corresponds to similarity as you and I might think. So now that we have a space where distance is semantically meaningful, finding the closest images is in some sense finding the most related images. Now, using nearest neighbors, we can find images in the collection that closely resemble the image that you fed it, the query image. So in this case, we get this nice little Egyptian dog from the Metropolitan Collection. So this algorithm works pretty nicely. You can kind of take any photo from your Instagram, and this is one that we're working on, and find really interesting artworks that kind of match what's going on in your life. And even when it doesn't work, here's Tupelo the cat, we find that the results are kind of stunning and ridiculous and hilarious. And so although this isn't quite what you'd expect, it's not quite wrong either. So we can kind of see that there's something going on here. It's picking up not just on the content, not just on the visual aspects, but a little bit of both. And so this particular algorithm is a really simple way to do deep image retrieval, but it doesn't really answer our question of what if we want to find the closest match by a particular artist, like Rembrandt. It's difficult to know where to start to hone in to just a particular class or subset of the collection. And for that, we'll need to develop some new machinery. In particular, what we want to hone in on is how do we actually find these k-nearest neighbors? And then we can modify them to restrict their attention to specific sets of points. The basic gist of efficient k-nearest neighbor search can be thought of as taking the space of points and partitioning them to form a kind of tree. This tree will make querying much more efficient. And there's a variety of ways to do this fast nearest neighbor search, but we focus on tree-based methods because these particular methods have a natural way to condition or restrict their attention to subsets. So here I have a query point shown in red, and I have a bunch of points shown in white in some high-dimensional space. These are kind of images, the features, and they're just here represented in 2 dimensions. So if you wanted to find the closest white point to that red point, you wouldn't start all the way at the bottom of the page. You kind of look at the points that are close to the red point. You'd take a little ball around the red point and only look in that space. So this is kind of the intuition for the algorithm. This is called the ball tree, and what it does is it takes the points and it splits them up recursively and draws a ball around these points. Far away balls, you're able to prune from your search because you know that every single point within that ball is just too far away, using mathematical techniques like the triangle inequality or the Cauchy-Schwarz inequality if you're dealing with inner products. So you can do this recursively, each time finding more and more balls that you're able to throw away because they don't contain relevant points. Eventually, you'll get to a point where there's a small enough number of points in your tree that you can actually just search through them with brute force search to find the closest point to your given query point. So as a recap, we can take a bunch of points and we can recursively split them up, form a tree-like structure of these balls, and this will help us perform queries. It will help us hone in on the exact neighborhood of our query point so that we only need to look at a very small number of points and save ourselves a lot of time in the comparison. However, the data we have doesn't just exist in a vacuum. There's a lot more to it than just the features of the images. For instance, we might have labels of genre, or class, or medium, or artist. So as a stand-in, we'll use color here in this example for a nice simple example. So I've colored these points in the tree based on, say, what genre of art they are. On the right, I've colored the leaves of the tree based on which labels they contain. So as you can see, this coloring of the points induces a coloring on the nodes of the tree. Now, if I want to ask a question like, can you find me the closest blue point to the given red point, I don't need to search through the entire tree. I can quickly prune most of the nodes of the tree and just look at the nodes that have blue points within them. And this is sort of the basis of the algorithm. What we want to do is we want to take a big k-nearest neighbor data structure and find a way to efficiently prune it on the fly for any given kind of subset or class that we might want to restrict our search to. So the natural question is, how do we actually prune this tree? For this, we'll take a page out of an algorithm called Elasticsearch. So what Elasticsearch does is it's a way to organize your documents and make search engines on top of your documents. So say you have a collection of hard-hitting news items that you want to be able to index and pull up based on keywords. Which Elasticsearch does is it forms what's called an inverted index. It takes all the words of the documents and it maps them to which documents contain those words. That way, when you search for something like tiger, you can immediately, using a hash map, get all of the documents that contain the word tiger. If you wanted something like tiger and king, you can take these sets of documents and intersect them to find all the documents that contain both tiger and king. Likewise, if you wanted tiger or king, you can take their union. So in this case, the logical predicates that you use in search, namely and or and not, they correspond to set theoretic intersection and union operations. And this lets you take some complicated logical query and really quickly retrieve all of the documents that satisfy that query that you gave to the search engine. And so this is the basis of technologies like Azure Search and Google Search, and it really helps you pull up large corpuses of documents incredibly quickly. And so in our particular case, we don't just want to filter documents, we want to filter the nodes of the nearest neighbor tree. So in this case, instead of documents, we now think about an inverted index from conditions or subsets to the parent nodes of the tree that remain after pruning. Here, in this example, let's say I want to restrict my attention to just yellow nodes. I can really quickly get all of the remaining nodes by using our inverted index and see that we have our exact subset of the tree ready for querying. So now that we have kind of a method to modify the k-nearest neighbor data structure to support conditions or subsets of the retrieved images, we can now swap out that piece in our original architecture. Now, with this new algorithm, we can add in additional types of conditions. Here, I'll show the closest results for paintings and ceramics and also cultures, namely Japanese culture. So as you can see, you can kind of find the closest match to that given dog, but in each one of these different conditions. And we recently just found this cute little Japanese Netsuke, and we were really excited when we found this little cute image here. Now that we have a method to find us the nearest neighbors for a particular class of objects, we can take objects in the collection and see what their equivalent objects are in different cultures and media. So here we have an example where we start with a Ming Dynasty porcelain blue and white vase. And we can find its closest textile. In this case, we get a double-faced banyan from the Netherlands. And what's more, we can go and even ask a more outlandish question, like what's the closest musical instrument? And when we actually asked people this without showing them the answer, they kind of took a look at that photo and said, I don't know, maybe a cello? And so we were really excited when we got a porcelain violin. We didn't even know this was in the collection. You can clearly see that the shape of it almost kind of matches the bowed out bottom of the dress, and the colors and the texture are almost identical. And these three things are not coincidences. They actually are indicative of a much greater cultural exchange going on. In particular, the Dutch frequented Japan and Jingdezheng, China, and took porcelain and exported it back to Europe. And this created sort of a craze for that classic blue and white pottery that you see all over the Netherlands and also all over China. So this is really a snapshot of a broader intercultural exchange between the Dutch and the Chinese and a variety of porcelain makers from around the world. For another example, we wanted to see how different works kind of evolve throughout time. So here, what we start with is a painted panel of Tatiasid, a figure of reverence in 800 BC Egypt. And we can kind of find its closest match in the Italian collection. We find, again, a figure of reverence, David. And you'll note that they share a lot of common visual attributes, namely they're symmetric. They're framed by this kind of arch. Winding the clock forward a little bit, we can see that the closest Chinese match is this particular textile of the Buddha. Again, perfectly framed and symmetric with an arch. And finally, the American equivalent of this particular archetype is George Washington here, another figure of reverence, perfectly framed, symmetrical. So what this really speaks to is that we tend to design these ornaments of reverence in a common way. We find symmetry and framing very important throughout our culture. You know, this isn't just something that happened in the American Revolution. It goes all the way back for the past 3 millennia. It kind of speaks to a common thread that we've all been designing off of for a very long time. So here, it's kind of a larger scale of some of the matches that we found. You can do this with really any match of the collection. So some of the fun ones that I want to point out is this particular image over here of the blue crane in the top left. When you try to constrain its match to glass, you find this crazy looking drinking glass over here. That's actually called a swan-necked bottle. So it takes the metaphorical and really makes this literal. So the goal of this project is not just to find cross-cultural connections for ourselves, but to really create a tool such that art historians and museum goers alike can explore the collection in new ways for themselves on their web browser. To this end, we take this research and we've created a website to help users explore this. We released this today and call this Mosaic. You can access it by going to aka.ms/mosaic. So let's check it out. Here we have the landing page, and we can see that a random artwork has been selected from the collection, portrait of a girl dressed in blue, and we can see the closest matches in the ceramics collection. You can filter by various different cultures or mediums. So here we can take a look at some of the closest matches in the Japanese collection, or we can find the closest matches in, say, the American collection to find artworks that really have the same kind of semantics. And for any given work, we can kind of check out the original source at the Metropolitan Museum, kind of figure out why these particular 2 artworks matched using SHAP, and explore matches for ourselves using this new artwork as a particular starting point. And so here we can kind of explore, say, closest work of ceramics. In this particular example, it's retrieved an Italian ceramic artwork that has a similar scene of a variety of people. And so let's say we wanted to jump to a completely random area of the collection. We can do so over here. I can search for something like a turkey. And we can see, using Azure Search, a variety of different turkey-style images. We can kind of pick one to start our next journey with. So we can kind of like this turkey dish over here. And now we can subset based on various different cultures. So we can find the closest Chinese turkey, and we see that it's this figure of a crowing cock with kind of bright feather ornamentation. And we can also take a look at various different mediums. Here we can see this this Dutch print, and we can go to the underlying source at the Rijksmuseum at any time to learn more information about this particular work. This website was built by a fabulous team of MIT externs over the course of just only 1 month, and so I definitely want to give them a shout out. Thank you very much to Stephanie, Mindran, Ben, Felix, Darius, Maggie, Marina, and Johnny for all of your hard work this past winter. This team really hit the ground running with no prior experience in this kind of work and was able to create a great website to help explore and make this research more tangible. So we've shown you how the algorithm works and some of the results that it returns. And we now want to get a better understanding of how this algorithm performs. Is it faster than brute force search? Is it performant? Does it scale to other data sets? And so that's really what we'll tackle in these next few slides. So the first particular aspect of this is evaluating the speed of conditional k-nearest neighbors. Is this even worth it to go through all this trouble of modifying the tree and creating an inverted index? So to kind of quantify this, what we want to do is compare this pruned tree over here, this tree that we've made on the full data set but pruned using our inverted index, to a tree that's made specifically for the task of this individual subset. And I should mention that this tree on the right will always perform better. It doesn't have to look through as many points, but it takes a long time to make that tree for every subset. It takes around 3 orders of magnitude more than just querying the tree. So it's a very expensive operation that we hope to avoid. But we hope to really get our performance as close as possible to this tree. So here we have a graph of kind of how this performs as a function of the size that you'd like to reduce your query down to. So on the x-axis, I kind of have the size of the data set as a percentage here. Over here on the right, we have basically an unconditional k-nearest neighbor search. And over here on the left, we're dealing with 1% of the data that you're looking to restrict your attention to. And these solid lines here, when they get close to their corresponding dotted lines, this means that the performance of the conditional solution matches the performance of the specific tree that's built on the subset. And this green line here, this is representing brute force queries. And so at a high level, what you can pull from this graph is for larger subsets down to about 1%, this is much more efficient than brute force search. And also it kind of approaches the best case scenario of designing trees for each individual specific query. However, you don't need to incur the incredibly steep overhead of actually making all these different trees. You can get this simply by querying an inverted index. And we put this table up here for reference. We've done this on a lot of different data sets, not just the Met and the Rijksmuseum, and we find that this trend holds globally throughout them. And you can definitely check out the paper that we've attached on the side for more information. So in addition to understanding how this algorithm performs in terms of speed, we also wanted to get a handle of how this algorithm performs in terms of quality. We wanted to find a way to understand, is there a way to improve this algorithm and measure its improvements quantitatively? So my advisor Bill, he suggested that what this algorithm is really doing is it's performing style transfer in a sense. When you take the image of the swan and you turn it into glass, in some sense, this is kind of like applying a style to it. Although this style is really non-parametric. It's formed by taking another image in the actual data set. It's not drawn on or modifying the original image. It's fully data-driven. So to evaluate this method, we've created 2 new data sets where we know the content and the style. This way, we can perform conditional image retrieval across different styles to make sure that the content remains the same. To help evaluate these kinds of conditional image retrieval methods, we've released the conditional art dataset, with over 1 million color images, 5,000 content from MS Coco, and 200 styles from the WikiArt dataset. We then take adaptive instance normalization style transfer and stylize each content image with the requisite style from the WikiArt dataset. This gets us this huge array of images where we know the content and the style of each one so that we can evaluate conditional image retrieval methods. And as a human-created baseline, we have the conditional font dataset. This one uses letters, kind of glyphs of the English language, as the content, and fonts as the style. So in order to actually make quantitative evaluation out of these data sets, what we do is we pick an image, we pick a style, and we ask, does finding the k nearest neighbors conditioned on that style return us an image with the same content that we originally picked? And if we recover that same content, then we have a successful algorithm. When we actually perform this analysis, we find that it gets much better than random. If you were to randomly pull images, you'd only hit the right image about 0.002% of the time. However, if you were to use a conditional image retrieval method, you get the right answer about 60% of the time, which is considerably above random. So we can kind of see that this is implicitly performing this non-parametric style transfer. And we also have a way of evaluating the quality of the embeddings used in the method. So the images I've shown are from ResNet 50, but through this analysis we've seen that DenseNet, SqueezeNet, and Mask RCNN might provide better embeddings for more relevant non-parametric style transfer and visual analogy methods. So we've seen how we can find these kind of visual analogies in the Metz and Rijksmuseum collection. But often when we get these analogies, one of the things the curators ask is, why are these two images similar? Can we actually explain what the algorithm is doing underneath the hood? So here I have a query image and a retrieved image, and it's not quite clear what's going on here. You know, it might be looking at the clothes, it might be looking at the arm, it might be looking at the pose of the body, the hair, the head. It could really be anything. And so what we wanted to do is create an algorithm that is able to answer that question of why do these two images match? So to create this algorithm, what we did is take tools from the existing model interpretability literature. So there's a fairly successful algorithm called LIME and another algorithm that came after it called SHAP. And these tools are really successful in interpreting image classification or regression systems. And while we don't quite have a classification system, we'll see later how we can kind of massage it in order to transform it into a classifier. So as a brief introduction to model interpretability, we have here a leopard classifier that is able to take a photo and spit out the probability that there is a leopard in the image. So in this particular example, we can clearly see a leopard, and we can clearly see that there's a high probability. So what LIME does is that it takes this image and it perturbs it. It randomly turns on and off splotches of the image. And the basic intuition is that if you happen to turn off the leopard, you should see that your algorithm has a dramatic hit on the probability of there being a leopard. So in this case, if we, down here in the bottom, censor the leopard out, the algorithm is no longer going to say that there's a leopard in there. So from this, we can get a rough understanding of which pixels and groups of pixels are actually important and actually contain the leopard. We do this by creating a locally weighted regression and looking at the actual weights of this regression. And when it's all said and done, you find that the groups of pixels that correspond to that leopard really light up in this regression. And so these are the actual pixels that explain why this particular classifier spit out this particular label. So to apply this to our particular analysis, we can kind of take a step back and draw this out schematically. We have an image, we feed it through a classifier, we get what's called probability logits, and we apply this model interpretability technique that randomly turns on and off pixels, or in SHAP, performs a game theoretic computation in order to find the pixels that correspond to our classification. With this approach, no matter how you build your semantic retrieval system, you're able to transform it in such a way that you can apply the algorithm LIME and SHAP to it to understand why it's viewing two images as similar. Really hone in on the pixels that make these two images similar. So when we go back to our original example and we apply these kinds of techniques, we can see some really striking results. Namely, on the conditional image that's constrained to the drawing category, we see that the algorithm is really picking up on the flowing robes of these two images. As you can see, they're lit up here and here. Say if we have a different conditional match, like this one constrained to lie in Tibetan culture, we were actually surprised that it wasn't looking at the robes so much as it was looking at the shining leg that's kind of in a similar position in both of these. So this is kind of an example about how these two different rationales for the matches can be disentangled and elucidated by using a model interpretability framework. So, as I mentioned, this is kind of a generic transformation that allows you to use anything from the model interpretability literature applied to this task of image retrieval. And so we can just take all of these methods and compare them. And here we show this in a chart. You can begin to see that methods like SHAP tend to find more important types of pixels than LIME, roughly speaking. And that's because SHAP has a set of formal guarantees that kind of guarantee that the interpretation you have is unique and satisfy a bunch of nice mathematical conditions. However, we wanted to actually understand which one was better quantitatively, as opposed to just relying on our qualitative instincts. So to actually evaluate these kinds of image retrieval interpretability methods, we play a simple game. We take two images that are really close together, let's say two photos of Lex the Pomeranian here, and we see that they're really similar. They're roughly a 95% match, say. Now, we interpret this match, we're able to get a heat map over the pixels, where the hottest areas are the ones that are most important for the similarity. And you can see that it clusters around Lex's head here. We then censor these most important, say, top 20% of these pixels. We should dramatically affect the similarity of these two images. You know, down here, this censored image, it looks more like a hairy log than it does a dog, and we hope that the similarity between these two images will take a pretty big hit with this censoring. So here we can see that the similarity really drops to something like 40% when you censor these top 20% of the pixels. So this gives us a kind of formal way to understand the importance of the pixels that these different interpretability methods are selecting. Namely, that if we remove the top 20% of the pixels, it should have the largest effect on the image similarity. So by doing this for hundreds of different matches, we're able to kind of get a rough sense of the quality of each one of these induced image interpretability methods. So we can see that the methods like kernel SHAP and partition SHAP actually do perform a lot better than LIME and other methods in the literature. And this really is kind of coming from the formal guarantees that SHAP provides. So finally, I want to take a bit of a detour to a different area of thinking about this algorithm. And the idea comes from the fact that these k-nearest neighbor data structures really tell us something non-trivial about the space that we're applying them to. In the literature, these days, k-nearest neighbor data structures can be improved by using unsupervised learning techniques. If you split the points in your ball tree based on k-means clustering or based on splitting on hierarchical PCA, researchers find that you can perform a lot better than just splitting using a heuristic. So in some sense, the data structure that's induced will perform a lot better if it actually captures the variance in your data set. So if we think about it, we can use k-nearest neighbor data structures as sort of a microscope to understand our data set and understand how our conditions are scattered throughout our data set. So here I have a visualization of the Metropolitan Museum of Art's k-nearest neighbor tree, and specifically which nodes of the tree contain American artworks. And as you can see, it's kind of clumpy. You know, you have these big splotches of red where there's no American artworks, next to big splotches of blue where there's a lot of American artworks. So we can kind of formalize this notion where if we take a look at how many of these nodes are red, aka don't contain any American artworks, about 41% of them don't contain American artworks. If we were to randomly shuffle the labels to kind of ensure that American art is homogeneous throughout the space, we'd see that we can only prune 12% of the labels. So in some sense, this is measuring the difference between these two distributions, the difference between American art and all the art that exists. And this measurement of the difference between these two distributions is very fine-grained. You know, we can see it visually. We can see where there are no American artworks and where there's a plethora of American artworks. And this is a very useful tool. And in particular, this has very useful applications to generative adversarial networks. And as a brief introduction to generative adversarial networks, these are a class of algorithm that are designed to dream up fake data, more precisely to sample from complicated probability distributions, like a probability distribution over faces. So the way that these methods work is that there are two parts, a generator and a discriminator. And the generator's job is to dream up new faces, and the discriminator's job is to tell the difference between fake faces and real faces. These two algorithms battle against each other for many, many hours, and eventually the generator gets so good at creating faces that they're almost indistinguishable from real human faces. And so these are two examples from a paper called Progressive Growing of GANs for Improved Quality, Stability, and Variation, and was really one of the first GANs to achieve almost indistinguishability on these generated faces. But as many researchers have found throughout the years, that GANs can produce really stunning faces, but these faces tend to have systematic biases. They don't properly account for all of the variation in the data set. You know, people find that these faces tend to be really aligned with the majority class of the data set. So what we wanted to do was see if this kind of k-nearest neighbor data structure can tell us a little bit more about where these algorithms fail, where they're actually avoiding in the data set. So as a brief explanation of the experimental setup, we form a data set based on the training data of one of these generative adversarial networks, data set called Celeb HQ. This is just a bunch of pictures of various different celebrities. And we also take its outputs, all of these fake dreamed up celebrities that the algorithm is producing. So we'll color them in the tree. Blue nodes tend to have a large amount of algorithm outputs, and red nodes tend to just contain the real data, don't really have any close matches from the algorithm. And so we can actually perform a little hypothesis testing and find the nodes that are most statistically significant. And we see that there's a huge amount of structure. There's this giant kind of blue rib that runs down one side. This is an area where the GAN is really good at creating images that look like real data. But everywhere else, there's huge areas of red, which means that this GAN is systematically undersampling this particular region of the data. And if we just look at some of these areas where the GAN is systematically undersampling the data, we find some really stunning results. So here I've taken a few representative examples from one particular node with a high discrepancy. And we can see that all of the people in there, one, are male, and two, they all have microphones. And I've just shown 4 examples, but literally every single example in this node had a microphone in it. And if we look at the kinds of samples that are pulled from the GAN that are close to these photos of microphones, they can't even draw a microphone, and they also have significant visual artifacts. So it kind of shows that the GAN is really struggling to hallucinate these microphones. It's something that isn't in a lot of the data and is kind of hard if it's just used to drawing faces. Likewise, one of the other nodes that we found that had a lot of high discrepancy had a ton of samples with cowboy hats, so these big brimmed hats on. And when we look at the representative fakes from this particular node, we see that they really struggle to generate the hat, and they have, again, these really significant visual artifacts that make the faces look downright terrifying. So this particular method allows you to find these areas where the GAN is really generating bad images, so that you can kind of better diagnose and understand where your GAN is particularly failing. And this has kind of become an interesting topic in AI fairness, where you want to make sure that the GAN is pretty good at generating everything, not just the majority class. So in summary, we've seen how conditional image retrieval methods can do things like find cross-cultural connections in the Metropolitan Museum of Art, and also help us diagnose biases in generative image networks. So with that, I thank you all for listening, and want to give some thanks to my advisor, William Freeman, for all of his help and comments, our great MIT externs who worked for a month to create the website aka.ms/mosaic, the Nerd Garage team who helped organize this effort and connect us with the externs, and to Scott Lumberg, Chris Hoder, Anand, Lei, Al, and Ryan for all their help throughout the project and for getting us in touch with the Met and the Rijksmuseum, who graciously open sourced their collections so that this work and a variety of other different technological work in the space of the arts is possible. Hi everyone, this is Mark Hamilton. Thank you very much for watching, and this starts the portion of the talk that's kind of the live Q&A. So you guys have been asking some amazing questions throughout this, and we really appreciate that. And so we'll be kind of going through some of the questions that we feel might be most helpful to everyone in the call, and answering them with a little more detail. So one of the first questions that I want to touch upon is one that a lot of different people asked in various different formulations in the chat, which was, can this approach be applied to different domains, biomedical images, satellite images, 3D images, videos? And I think the short answer is yes, as long as you have a good way to featureize your data. It doesn't really matter what kind of data you use, so long as your features are, and the distance between the features is representative of what you would like. In our case, we wanted to make sure that the distance between the features really corresponded to high-level visual similarity. And when you use features where the distance corresponds to something meaningful, the algorithm becomes meaningful as a result. And so another great question that is along this vein was, can you use this approach could you trade off between visual similarity and something else, like subject matter or texture or color? And so the shorter answer is yes, that when you use a different set of features that maybe prioritizes something like patterns or style or color, your resulting matches will prioritize that as well. So one explicit example that we kind of mentioned in the paper is that if instead of using the features from ResNet 50, if you use the features from a style transfer network, like adaptive instance normalization, what you'd find is an algorithm that threw away the contents and really just cared for stylistic visual analogies. So there's a lot of different ways you can kind of manipulate this problem to get at what you want. Another great question that got brought up was whether this approach could be applicable in the streaming scenario. Now, while this work didn't explicitly target the streaming scenario, there are a lot of works that do aim to build up nearest neighbor trees in the streaming scenario. And so you could imagine, because this approach really applies to any nearest neighbor tree that you build, you can imagine keeping track of the information in the Elasticsearch index as you change the information in your tree. So it would involve a few modifications and tweaks, but I think fundamentally this kind of approach is possible. And if you want more information, you can definitely feel free to reach out to us. Let's see here. Another great question was really asking to clarify the interplay between the two different kinds of indexing methods that we use, namely the Elasticsearch inverted index and the ball tree from K nearest neighbors.
To dive into a little bit about what the interplay is that we're not just using one or the other. We're using a hybrid data structure that uses the ball tree or the k-nearest neighbor tree to organize the spatial information and uses Elasticsearch to organize the conditional information. And it's not just using both of these indices at the same time. Elasticsearch's documents are actually nodes of the ball tree. So there's this kind of, they need to be plumbed together in the correct way. And what this allows you to do is really quickly prune the k-nearest neighbor tree to fit your particular logical query that you have give to Elasticsearch. So it kind of tethers these two algorithms together and allows you to get sort of the best of both worlds. Also had a few questions that were really tend to follow the theme of what about other kinds of model interpretability methods. So one question was about model activation visualization or saliency maps. And another question was about layer-wise relevance propagation and deep lift. So these three things are all different kinds of ways to interpret classifiers or regressors and could be applied to interpret similarity networks by doing the same kind of transformation that we apply to bring LIME and SHAP into the similarity network interpretation space. So what I mean more specifically is that you kind of take your similarity network and you do a transformation to make it look like a classifier. It spits out a similarity score and takes in a single image and compares it to your result image. And with this, you can apply all the tools from the model explainability literature, like activation, visualization, or layer-wise relevance propagation or deep lift. And I should also mention that SHAP kind of generalizes some of these approaches. So I'm pretty sure it generalizes deep lift and others as particular, more specifically, deep lift is a particular approximation to additive Shapley values. And that original additive Shapley value paper goes on to say that additive Shapley values are kind of the unique ways to interpret your model in such a way that it has a lot of mathematical guarantees. So it's a very interesting space there. There's a lot of interplay and a lot of different methods that all seem to be getting at the same kind of idea, but through various different ways. And so it's exciting to be able to work with all of them at the same time. I'll look at some of the other questions now. This is a great one. Is there a way we can improve the bad images generated by the generator, which were trained by the image of people wearing hats or images having microphones along with the face? So this question really aims to get at, now that we know that there are bad images in the collection, that the generator is particularly bad at creating certain areas of the collection, can we fix it? And I think that yes, as the short answer is that, you can imagine a whole different barrage of different ways to intervene to fix these issues. And one of my colleagues at MIT, David Bao, has a nice paper where he even shows that just adding in random conditions to a network can improve its performance on these particular areas. So that's kind of one way that you can fix this, is that if you have knowledge that there are microphones or particular aspects that the algorithm is not getting correct, you can consider making a conditional GAN. And the mere fact that you give the condition kind of forces the GAN not to be able to wriggle out of generating these images. It kind of says, no, you have to generate an image with a microphone. And the discriminator knows that in these conditional GANs, it knows what the conditional information is. So it knows that I should be looking for a microphone. And if you don't make a microphone, then you're not a very good generator. So adding conditional information can be one way to improve the performance of GANs. And really more broadly, I think in the spirit of GANs, at any way you can discriminate the real data from the fake data is theoretically a signal that you can use to train the method. So the more ways that we can figure out how images that are generated are different from images that are real, the more kind of modes of signal the discriminator could use in learning for future algorithms. Okay, great. Here's another great question. Is there a way to get the conditional network working when we don't have ground truth labels? Can features be learned? Like in recommender systems, can we learn features of images of movies and users? This is a really great leading question. And again, the short answer is yes, definitely. There are a wide variety of methods you can use to learn features for data that don't require any labels at all. I posted one answer that kind of answered a similar question in this realm. Pointed the asker to SimCLR, which is a recent paper by Jeff Hinton's group that beat even supervised pre-training. So it's even better than using the labels in ImageNet. So what this approach does is the basic idea is that you can take any image data set and learn to understand it without labels by playing different kinds of games with the images. So you can randomly flip the image and tell the algorithm to predict whether you flipped it or not, or randomly change the color, or randomly make it brighter or darker, and ask the algorithm to determine what went wrong with the image, what you did to it. Or even to push these images with similar transformations together and with different transformations far apart. So what these various different kinds of approaches allow you to do is effectively learn really good features that correspond to high-level similarity, like the resonant 50 features, but without any labels, so that you could apply this directly to your satellite images or your biomedical data or whatever crazy data set you have that doesn't necessarily have labels. And also, this asker mentioned recommender systems. And this is a really good other way to get features, that you don't need to just get features from one of these vision networks or a game. You can also get features from really anywhere that they crop up in machine learning. So recommender systems are a particularly good area where these low-dimensional features that represent users and items crop up quite naturally. And so you could consider exploring that. Here's a good question. Is the KD tree method similar to Annoy and FAISS? Yes. Annoy and I'm not quite sure about FAISS, but Annoy specifically is an ensemble of trees approach. So it's an approximate nearest neighbor method. It's very fast, and it uses an ensemble of random projection trees, which are a slight variant of KD trees, to store the data. And basically it traverses these trees in parallel, and it doesn't exhaustively search for the closest match. It just finds a good match after a little round of exploring the tree. So in the future, we hope to integrate it with Annoy. And if anyone knows, if anyone's familiar with coding in Annoy, we'd love to, help them add this to Annoy, because it's certainly one that we use a lot over here. And I think there's a follow-up about FAISS, and so I guess specifically the information that you might want to ask when approaching a new nearest neighbor method is there's three main types of nearest neighbor methods. There's hashing-based, there's tree-based, and there's graph-based. And so our research applies mainly to tree-based methods. And these other two approaches, graph-based and hashing-based, are a little bit harder to move into this regime, although we won't say impossible, because who knows what future research can hold. So I think that the applicability of this to FAISS would really depend on, is FAISS tree-based or is it graph or hash-based? If it's tree-based, then you could imagine integrating this with that system. One other interesting question that might be good to discuss is that someone asked if we were using Euclidean distance, and the answer is no, we don't use Euclidean distance, and it's for a particularly interesting reason in that Euclidean distance is particularly bad in high-dimensional spaces, that Euclidean distance is not very robust to in high-dimensional spaces. It really changes its fundamental way of working. It's completely dominated by outliers and things like this, whereas cosine distance or angular distance, basically the angle between 2 points, is much more robust in higher dimensional space. And this angular distance is very related to the dot product between vectors. And so the angular distance, more formally, is the dot product between two normalized vectors. And researchers find that this angular distance is just much more robust in higher dimensional spaces and really captures the geometry a lot better than Euclidean distance. So there's a few different papers about why this is the case, and there's also a few blogs out there, if you Google this topic, that have some really clever visualizations to help you understand. And really the moral of the story on this problem and across a variety of machine learning is that high-dimensional space is very different than low-dimensional space in ways that are completely surprising and unintuitive. And one of my favorite examples of this that's somewhat related, but is that the Gaussian, the bell curve, the standard normal distribution, fundamentally changes in high-dimensional space. That in low-dimensional space, the bell curve looks like a bell. And in one-dimensional space, it looks like a bell. In 2 dimensions, it looks like a hill. In 3 dimensions, it looks like a ball. In 4 dimensions, it looks like a 4-dimensional ball. But in high dimensions, it looks like a thin spherical shell. It fundamentally changes its shape in a very astounding way. And so, this is just one particular example of how high-dimensional space gives a lot of complexities arise, and also explains why these lower dimensional features that come out of these networks tend to perform a lot better, because they avoid some of the difficulties in high dimensional space. All right, and I guess that pretty much covers a lot of the main questions. And for others who want to learn about kind of more details, you can definitely check out our paper in the right-hand side in the sidebar. We have a live website that you can go to actually play with and explore this algorithm. The code has been open source, so you can check that out as well. And definitely feel free to get in touch with us. My email is on the slides, and it's probably not too hard to find me. And thank you all for coming to this webinar. We really appreciate you taking the time out of your day, and we hope that this was helpful to your work and your research. And if you want to get in touch to collaborate or to recommend other references or use cases, please feel free to do so.